The next speaker is Dr. Azade from Durham University. She will speak about build-up of Milky Way satellite, Milky Way stellar halo, the revolution of Gaia. Sorry, I need my glass.
Well, hi everybody. Sorry, now that I'm in full screen, I can't properly see the room. It's my pleasure to be here today with you, talking a little bit about part of my work in the last few years. And thanks for the invitation from the organizers. My name is Azade فتاحی. Some people call me Azzy, and I'm an assistant professor at Durham University in the Institute for Computational Cosmology. And I will be talking today about the buildup of Milky Way's stellar halo, especially that this field has been made a lot of progress in the past year or two or three, thanks to the Gaia observations. Before I jumped into that, this is just a teaser because it's also related to what Indranil was talking about. We had this review article that came out 2 days ago on AstroPH, and it was released by Nature Astronomy at the beginning of the week. If anybody's interested in topics related to the tensions of lambda CDM with dwarf galaxies, maybe you have a look at the article and how we kind of try to go back and reclassify some of the tensions, what things are tensions, what things are uncertain. But that's not what I'm talking about today. This was just a quick teaser. To recap and bring everybody kind of on the same page of why we are interested in studying the stellar halos and what is the theoretical framework behind that. And before I kind of jump into some of the observation results that we have found or the community has found in the recent years. In the standard model of cosmology, lambda cold dark matter, cold doesn't have to be super cold, even if roughly warm. Most of the things I'm talking about still holds true. In this framework, basically we know from the CMB, we know about the initial condition of the universe, about how much dark matter, dark energy, and ordinary matter exist in the universe. And in this framework, we start from a big bang, the universe expands, and the structures form from the initial fluctuations in the matter density. And we study these growth of structures mainly using numerical simulations. Basically, after early on, after high redshift, essentially early universe, the growth of structure is non-linear, and in order to study galaxy formation and internal, for example, structure of dark matter halos, we need these numerical simulations. And the bottom of the page, hopefully you can see actually the cursor moving around. In the bottom, you see a visualization of one of these simulations, as I mentioned, in the early on in the universe, which is on the left. We have some fluctuations in the matter density, and then they grow and form the larger scale structure and the halos we know today. This is a hierarchical formation of structure, which means smaller objects form, and then they accrete and merge together and form bigger and bigger objects. That is a key component of formation of stellar halos that we will be touching upon today. So basically with stellar halos, we can probe the hierarchical galaxy formation. And because movies are first of all fun, plus they will easily show what this hierarchical formation means. I'm going to show you a movie. I'm going to press play, but to tell you what you're looking at here, you're going to look at the formation of a galaxy like Milky Way or a halo of a Milky Way. You're seeing the dark matter distribution on the left, the gas density in the middle, and the stellar light on the right-hand side. This is from the Auriga simulations. And what I particularly would like you to note is basically the many smaller dark matter halos which are accreted to the main galaxy, and they contribute to the build-up. And equivalently, on the right-hand side, we see their stellar components. that are being accreted to the Milky Way, and they contribute to the growth of the Milky Way and the formation of the stellar halo. In this particular movie, because basically the contrast is such that you will see the disk of the galaxy on the right-hand side, the stellar halo is not very clear, but you got the idea of basically all the little clumps that are merging to the Milky Way and get accreted and form the stellar halo that I'm gonna basically show you what they're supposed to look like in principle in these simulations. Again, in the previous movie, the contrast was set so you can see the disk of the galaxy. That's where most of the mass is. But if we mask out the disk of the galaxy and try to look at the kind of a diffuse light or diffuse mass around these galaxies, we are expected to see a diffuse component that is called these stellar halos, which are formed by the disruption of this accreted dwarf galaxies around a galaxy like Milky Way. These are some images from simulations. On the left, by the way, this has been known or suggested from early on, even when simulations were dark matter only, using particle tagging methods and semi-analytic modeling. People could model basically what the structure would look like. On the left, you see an example of that. And nowadays, with hydrodynamical simulations and galaxy formation simulations, we can actually also see these stars as actual stars in the simulations and the formation of the stellar halos. Something that is quite important and striking are the existence of all these substructures around the galaxies. By the way, I forgot to put a scale here. The scale that you're looking at here is about 300 kiloparsec or more. Basically, going from the center of the halo to the outer parts is about the virial radius of these halos, which is roughly about 300 kiloparsec. Striking things are the existence of these substructures. As you can see, this is not a very smooth distribution, because these different objects get merged with the main galaxy. We see all these different substructures. We see the same also in this hydro simulations that I worked on during my PhD. You see all these shells essentially and all these streams that are formed around these simulated galaxies. With deep observations since maybe almost 10 years ago, or actually more than 10 years ago now, sometime 15 years ago, I can see 28 here, we started to see with the deep photometry, we started to also see these substructures around observed galaxies we see. On the right-hand side, you see two example Andromeda galaxy and another elliptical galaxy with all the substructures as expected around them. You see all these streams and what people call plumes around Andromeda, the same around this elliptical galaxy. In these external galaxies, of course, we have a bird's eye view. We see things from, well, as an outside observer. Inside the Milky Way, we don't have the bird's eye view, but if you look at up in the Milky Way, there are some distance and metallicity cuts to make the stellar stream pop out in the image on the left, but that's how basically the stars in the halo of the Milky Way would look like, and we start to see substructures. This is from at the time of SDSS. This is pre-Gaia and other, and 10 years ago almost. This is SDSS times, where we could see Sagittarius stream, and maybe you've heard about some of these names, GD1 stream that goes, it's a very thin and longer stream, Orphan, PAL5, and Triangulum stream. So basically, we started to uncover some of these substructures that we would expect around Milky Way. Tell you a little bit more quantitatively about what we expect, about properties of these objects that form the stellar halo using the simulations. This is the work I've done mainly with the Auriga simulations. Just a quick introduction. This is a suite of zoom-in simulations of Milky Way halos, and there's about 30 of them. And some of the results I see, not some, almost all the results I show in the next 2-3 slides are based on this analyzing these simulations of Milky Way. It's from Grant et al. So in the simulations, we can trace essentially all the stars we find. We have the power to trace them back in time and know where exactly they come from, when they fall into the Milky Way. So basically, we have a lot of power in terms of understanding the origin of things we find in the simulations. So the way, basically what we do, or what I did, is you take each star particle and we trace them back to the dwarf galaxy that they came with. And then so I can know, if you look at the stellar halo of something like Milky Way, accreted object or accreted stars, where they are coming from which object. So I can start to classify these stars are coming from that dwarf galaxy that has been disrupted, and so on. Here is an example of one of these halos, and I will walk you through what you're looking at. You're looking at in the left-hand side, and this is only one Milky Way halo. Different lines are different dwarf galaxies that have merged and are accreted and merged with the Milky Way and formed its stellar halo in this particular case. And the different objects are color-coded based on how massive they are. The red colors refer to objects that are relatively massive in the dwarf galaxy scale. These are like 10 to the 9-ish in stellar mass objects. When we go to lower mass progenitors of these objects, lower mass means here about 10 to the 5, 10 to the 6 solar mass in stars. So I can look at basically where, as I identify which stars are coming from, I can look at basically how they are distributed. Here you can already see that this is the enclosed mass. Basically, most of the mass is dominated by these one or two relatively big objects, the red and orange-ish curves. There is a lot more objects that have got accreted and contributed. As you can see, there's many lines here, maybe, I don't know, 20, 30 different lines here. These are all these various dwarf galaxies that have been accreted and deposit their mass in the stellar halo. But their mass contribution is relatively low, and the mass is basically dominated by these two big objects. I can start to look at things differentially in radial bins, and what fraction of mass is coming from which object, which of these progenitors. I keep talking about stellar halo progenitors, so I'm talking about these dwarf galaxies that got accreted and disrupted. If I look at let's say in the inner region, let's say in the inner 20, 30 kpc of this particular case, I can ask what mass fraction in stars, what mass fraction is coming from that particular progenitor, from that red or high mass progenitor. You can see that almost, as perhaps you could guess from the left-hand side, most of the mass, about 80% of the mass, is coming from the most massive progenitor, and then maybe 20-30% from the next progenitor. The other interesting trend you start to see that the inner region is pretty much dominated by these big objects. But as we move out in the stellar halo, when we go towards outer skirts, we start to see other smaller objects also have notable contribution, going from almost 1% to maybe 10% in the outer region. The fact that the inner region is dominated by this one or two halos, we saw this in this halo, in this example. I want to show you how it would look like if you look at the ensemble of all these 30 Milky Way halos that we have. So you're looking at basically different panels here are different radial bins. You can see in the legend 0 to 20 kpc, 20 to 50, and so on. And this is compiling all these 30 Auriga halos. The x-axis is Auriga halo numbers. They're just different halos. And I would basically compute how many progenitors we need to build up most of the mass in that radial bin. In a previous case, we saw one or two were important, but here we see that almost this is true in most of these Auriga halos. You go from 1 to maybe 5 at max for forming the inner bits of the halo. So this has been also shown in some other works that I'm citing here from Beast et al. and Monakesi, that basically the inner regions of halos are expected to form halos, by the way, unless I say dark matter. When I say halos, I'm talking about the stellar halos. The inner regions of stellar halos are formed by very few dwarf galaxies. Very few dwarf galaxies is enough to form the inner regions. And as we go into the outer parts, as we move right in this panel, more and more objects are contributing to the mass. This is equivalent of what I was trying to explain here using one example, but this was kind of a representative example. Most halos basically behave this way. In the inner regions, you add up the mass of these 2, 3, you almost have all the mass. In the outer parts, you have to take into account the various objects. So something important to have in mind in the inner regions, we need very few dwarf galaxies. But what is for example, are these few equal mass objects, or one or two of them are very massive compared to the other? This is what I'm trying to show here. That on the y-axis, this is how much stellar mass is contributed from these different dwarf galaxies to a given halo, and what is the stellar mass of those dwarf galaxies that got accreted. And the top progenitors are marked with a filled circle, and you can see the top progenitors, which are basically the objects that formed most of the mass in the inner regions. They contribute a lot. They contribute, as again we saw in one example, but that's true. One progenitor is enough to form 70, 80, 90, in some cases almost 100% of the mass. And those progenitors are relatively massive. You can see about 10 to the 9 or so. Their stellar masses are about 10 to the 9 or so. The reason that the inner regions are so dominated by one or two big objects, but not in the outer bits, one important reason is a dynamical friction. Basically, when two objects that are merging together, they have similar-ish mass, or the mass ratio is close to 1, that looks like a merger, that looks like a major merger. The dynamical friction that is actually caused by the extended dark matter halo of these objects. The dynamical friction causes the objects to sink to the middle. That's why basically if you have a massive object, most of its mass, it's concentrated around the center and it forms most of the mass in that region, because dynamical friction causes the orbits to sink in towards the center. And that's why basically as soon as you have a big object coming in, merging to the Milky Way, the mass gets deposited, most of that mass gets deposited in the inner regions. So this is kind of the theoretical expectation we see from, again, these were said in dark matter only simulations with some simple modelings in the past. Now we can actually use it more properly with hydrodynamical simulations. And now let's make a jump to what we know from observations. By the way, many of the things I show are, of course, before the Gaia DR3, the data release 3 was done on Monday and Tuesday. And of course, most of the plots and results and papers I'm going to show are precursor to Gaia DR3. So things are going to change even more. So I'm going to give you kind of a summary of the bits that I and my colleagues and related people worked on prior to Gaia DR3. What's Gaia? This is an ESA mission led by Europeans, and Gaia is a space telescope that basically monitors the sky over time, and it has measured, or it will measure by the end of its mission the proper motion, parallaxes, photometry, and spectroscopy of a lot of stars in the Milky Way. It's about 1 billion stars in our galaxy. The very key thing is the statistics. We get a lot of stars. Very important thing is the proper motions. Basically, Gaia revisits the sky multiple times over its mission, and because of that, it can measure proper motions of all these stars. And then it can do spectroscopy of brighter stars, so it can also derive chemistry, some of the stellar properties like stellar ages, gravity, etc., etc. So it is giving us a lot of information about the stars that are around the Milky Way, at least around the solar neighborhood. One of the early, related to the stellar halo, one of the early big results that came out, some of you might have heard about the name Gaia sausage or Gaia enceladus. So I'll tell you a little bit what that is about, because that's a key point in the rest of the paper. What came out quite strikingly from I think even with Gaia DR1, it's when we plot the radial motions. Here you're looking at the circular motion on the x-axis. This is the circular motion of stars in the Milky Way versus radial motion. We can clearly see two different components. By the way, there is also a metallicity cut here, Fe over H of -1. So we don't get a lot of these stars. It goes towards lower metallicity, which are mainly stellar halos. Something maybe I should have mentioned, most of the stars in the stellar halo are lower metallicity objects because they are coming from dwarf galaxies. We see two different components. We see the galactic disk, which is spinning or have a circular velocity of about 200 kilometers per second. And we see another component that, I guess because of its shape, the Cambridge group, Vasily Filukarov and company, they call it the sausage. It's kind of elongated in this space, in this circular velocity, radial velocity space. It's kind of a squashed feature. And because of its shape, I guess they gave it that name. Kinematically, we can quantify what this elongated shape means. The elongated shape means the velocity dispersion in the radial motion is much higher than the velocity dispersion in the circular motion. You might have heard about an isotropy parameter. This can be quantified, and basically, if one tries to decompose this velocity space, this is squashed component that looks like, or has been named the sausage, has an isotropy of about 0.85. It's quite radial. In this beta parameter, 1, because of its definition, 1 means fully radial, 0 means equal motion between radial and tangential, and circular velocity is essentially beta of minus infinity. But beta of 0.85 means it's quite radial. To also give credit to the other people that at the same time, another group from Groningen, the previous plot was from the Cambridge group, another group in Groningen, Amina Helmi and her group, were also working on similar topics. They also identified this feature on a slightly different plane. This is now Vy versus Vx. This is almost tangential velocity versus the other component. They also identified the similar features, and they call it an enceladus. These two works kind of came out roughly at the same time, within a few months of each other. And now I will refer to that as GSE, as kind of crediting the work of both groups. So this feature that, by the way, hopefully it's clear that if you remove the galactic disk, well, the galactic disk is the disk, the rest of this object, well, they're not galactic disks, so they are the majority of the stellar halo stars, and they have very particular kinematic features. They're very radial. They have a high beta. Very early on with Vasily, we started to look at this in the simulations. Now I realize I should have met before going to the simulations. When chemistry is quite important. Basically, what kinematics alone is not enough. Chemistry is giving us a lot of information in identifying substructures in halo. Here is an example for this GSE or Gaia sausage, particularly.
آزاده.
Yes. Okay. We can see that they actually, if we move in chemistry, we are going to metal poor stars on the left, metal rich stars on the right. We see these elongated features mainly at higher metallicity. So metallicity has been quite important to identify these substructures. We went to the simulations and tried to see if we see similar features in the simulations. In this work, I basically looked the same Auriga halos that I was talking about before. I removed the disk. You're looking at the exactly similar plane, radial velocity versus circular velocity. This is the same plane as this one. Does it come up? Yeah, this is exactly the same plane as this one, just in different halos. We see some of them have these elongated features, some of them don't, and we try to basically identify the ones that have these features. We could identify about 7 or 8 of Auriga halos have such a, basically, their stellar halo is very, at least in the inner regions around the solar neighborhood, is very radial. So we identified 7 or 8 of these examples in Auriga simulations. And we could actually go back, look at the origins. Where are these very high radial stars are coming from? It turns out that basically most of them are coming from a single progenitor. So we could identify, at least in the simulations, we could identify their progenitor. We could ask, what was the stellar mass of that progenitor? What was the merger time of that progenitor? And this is kind of with a couple of examples. It's not a lot. I think it's about 8 or 9 points here. Each point represents one Auriga halo with features similar to GSE. We can see that these are relatively massive objects, about 10 to the 9 or so, that merge with the Milky Way. Well, it spans a range, but about maybe at the peak, about 10 billion years ago. 0 is Big Bang, 14 billion years is today. So they merge with the Milky Way about 10 billion years ago or so. And we can actually also see what fraction of the stars in the stellar halo are coming from that single progenitor. We see basically the way to read this plot, there's a 1 to 3 line, and there would be a 1 to 2 line if you wanted to imagine. There's 50 to 30% on average. 30 to 50% of the stars in the inner 20 kpc of these Milky Way simulations are coming from that single progenitor that formed the GSE. So that progenitor essentially is the main, I've checked them individually, that progenitor is the main progenitor, or the one that contributed the most, the main progenitor of the inner stellar halo in most of these cases. Something very brief, I don't go to the details because it's not the topic of my talk today, about the dark matter content of those dwarf galaxies and how much they contribute to the dark matter halo. The short answer, the dark matter contribution is way less. If their stellar contribution was 30 to 50%, their dark matter contribution is between 1 to 10%. I don't go into the details of why that's the case. The short answer is it's related to the stellar mass halo mass relation. Briefly, actually I'm going to skip this because of the time. I'm going to basically what else we this is a community now. This is not my work. Community has found in the stellar halo of the Milky Way the different substructures. There's a very beautiful work from Rohan Naidu that he actually defended just a few months ago at MIT. They combined H3 survey, that's a spectroscopic survey, with Gaia DR2 because the spectroscopy of Gaia DR2 wasn't as well. So they got the chemistry from H3 survey. When you try to combine chemistry and kinematics, these are some kinematics planes. You can see LZ, this is angular momentum in the Z direction versus energy of the orbits for stars. They are divided in different metallicity bins and also color coded by alpha elements over Fe. We start to see actually different features, different substructures in these kinematics plane, and also when we add the chemistry information, it comes out quite more clearly as well. So using this chemistry and kinematics, if you're interested, go look at Rohan's paper. That's very nice. They identify a couple of other more substructures in the halo. They have all these different names. GSE we talked about. Sagittarius was always a dominant one people had known from the beginning. It was clear in the CSS. But they also went on identifying a few other ones. And the mass contribution, they also identify the mass contribution from those objects. And as kind of expected from what we saw in the simulations, most of the mass is coming from GSE. This is the mass kind of fraction at different radii. Most of the mass in the inner kind of 20, 30 kpc is coming from GSE. In the outer parts, Sagittarius becomes important, but Sagittarius is thought to be a slightly lower mass than GSE. GSE is basically the biggest progenitor, and we have a few other substructures that again were predicted, and I think we're starting to uncover these substructures. A very brief mention, there are also stellar streams. These are, that I haven't worked on the stellar stream, I just follow the subject. Stellar streams are narrow, coherent, and cold, dynamically cold substructures in the halo. In the very original image you've seen, something like GD1 stream is cold, thin, and it's coherent. So it goes along its orbit. Just by looking at this stream in the sky, you would know where the orbit of the object is. Now we have uncovered, this is the work by Kiyati Malhan, who identified many more of these stellar streams. They are thought to be mainly originated from globular clusters because of their narrow and cold dynamics. They are thought to be originated from globular clusters. Now we have basically a lot more of, we have uncovered a lot, the community has uncovered a lot more of these substructures. And because of time, I don't think I'll have the time to go to the detail of my next slide. I'll give you the teaser, and please feel free to go and look at Tilly's paper. Tilly is my student here who has worked on basically based on what we know about the assembly history of the Milky Way. We know the GSE was the big merger that formed the stellar halo. We know about one or two other big objects that came to the Milky Way, and how, if we look at cosmological simulations with a big sample, she looked at ego, how common these assembly histories such as Milky Way are if you compare things with big simulations. I skip what the result is, but this is a teaser for you to go and have a look. And I leave you with my conclusion or some sort of a takeaway point. The takeaway points are basically inner halo or accreted dwarf galaxies form the stellar halo, and the inner bits of the stellar halo is expected to be formed from very few massive dwarf galaxies. This is a combination of, the reason is combination of dynamical friction and stellar mass-halo mass relation. When we go to observations, we see that the stellar halo is dominated by a highly radial component, that's the GSE. We think its origin is a massive dwarf galaxies that merged with the Milky Way about 10 billion years ago. There are some observational evidence, I didn't get the chance to go into that, there are some observational evidence apart from what we saw in the simulations, and that it merged with the Milky Way about 10 billion years ago. And of course, we have uncovered many more substructures in the Milky Way, and the punchline of Tilly's paper that I didn't go into is if GS is the only massive accretion that formed the stellar halo, and that is the only one, and the other accretions are not as massive, Milky Way's assembly history is unusually quiet. Unusually, not that it's whatever, it's a big issue, but we don't find a lot of the Milky Ways in these boxes that have such a quiet accretion history, which is, I guess, a question for the field about whether are we missing one or two other big substructures or not. And I'll stop here and take questions, if any.
Thank you, Azade. So, is there any question? Is there any question? Azad, I have a question. There is an idea that some globular clusters in the Milky Way are captured by the Milky Way from the dwarf galaxies.
Yeah.
What do you think about this process? Is it a efficient process in the Milky Way? How likely this process is?
Yeah, a good question. Actually, I wanted to talk about this, but again, because of time, there was none. There's already, again, thanks to Gaia, because we have proper motions, some of the dwarf galaxies, globular clusters around Milky Way have already been associated based on their kinematics, and a little bit, mainly kinematics, but a little bit also chemistry, but mainly kinematics. Some globular clusters are already thought or been associated to GSE, to Sagittarius, and to some of these big objects that are coming in. So there is, naively speaking, zeroth order from the theoretical point. You have this big, usually there's a stellar mass or halo mass, globular cluster number relation. So if objects are massive enough, they will have a number of globular clusters around themselves, which they will, when they will be accreted to the Milky Way, they will bring these globular clusters with them. So zeroth order, that makes sense. So, and interestingly, in the observations, as I said, there are some, and this is kind of the community, even those groups that compete with each other kind of agree that the set of these globular clusters that are associated with Sagittarius, GSE, and another one that another group suggested, Kraken, they call it a Kraken. We will see if that's gonna hold to be true dwarf galaxy that merge with the Milky Way. So observationally, it makes sense. And now, if you ask me what percentage of or what fraction of Milky Way globular clusters are coming from accreted dwarf galaxies, I don't have because general, but this is not my field. Take my answer with a grain of salt. I think the majority won't be accreted because this halo mass globular clusters count, or halo mass, stellar mass globular cluster count, tells us that dwarf galaxies would have, if any, very few globular clusters. Dwarf galaxies will have very few globular clusters. So I wouldn't expect that most of the Milky Way's GC's globular clusters are coming from dwarf, but definitely some of them have. How many? I don't know the exact fraction.
And is the resolution of M-body simulations, cosmological M-body simulation, is enough to check this process or not?
No, not at all. No, we don't. Almost none of these cosmological galaxy formation simulations, almost none, resolve star cluster formation, basically, and globular clusters. There are post-processing or basically some sort of a semi-analytic approach, if you're familiar with those, some sort of a semi-analytic approach that people try to, after the simulations are done, you can kind of attach where the globular clusters might be. So the short answer is no. In the galaxy formation simulations, especially the cosmological ones, there is no star cluster / globular clusters in there. The resolution and the physics is not there. Some of these are kind of ongoing works of those who simulate like individual galaxy or star formation or star forming region in an individual galaxy. So these are, most of them are not cosmological context. So you'd have very high resolution in a small part of a galaxy that is a star forming. Those start to resolve some star clusters, actually not even globular clusters. Those start to resolve that, and I think in the future, my hope is that that's actually what I'm hoping what my student who's coming in fall would work with, basically trying to take some of those super high resolution models and try to understand something about the star clusters and globular clusters and see if we can extend some of the cosmological runs to include some sort of a globular cluster model for them.
Thank you, Azade. I have a question regarding the GSE and some velocity dispersion outer layer of the galaxy. It may be the influence of the tidal field from the galaxy in vicinity of the subject. Is it true or something like that? Because the anisotropy and velocity and high values for beta in outer layer of the galaxy is somehow it seems that due to some influence of tidal fields on this galaxy.
Let me try to get the question right. So if the question is how does this how does anisotropy or beta profile look like in the outer bits? We don't have information too much in the outer bits because what the kinematic or dynamic information we have is about maybe at most out to 50 if you want to trust it so much. It's more like around the 20, in the inner 20 kpc, maybe then you got the 50 kpc. So the reason that this beta is very high is actually dynamical friction. This has been also shown in n-body runs, that because when you have a big object, the dynamical friction makes the orbit sink to the center and radializes the orbit very much. Basically, the beta of the stars are the signature of the last bit of the orbit of that progenitor. So that progenitor, the last bit of that orbit was very radial, and that's why when it gets disrupted, the stars that became the debris left from that objects have very high beta. And as I said, most of those objects, most of the stars are in the center, not in the outer parts. So we are not expecting that outer parts would have a beta of whatever, 0.8. If you go to cosmological simulations and try to look at the beta profile, beta is high in the center, and then in the outer parts, maybe it's about 0.2, 0.3, 0.4. If you want to get information from those. But from observations, we do not have that much information far out in the halo.
به فارسی خیلی ممنون که دعوت ما رو پذیرفتید. انشالله که حضوری در خدمتتون باشیم سال آینده.
خواهش می‌کنم، مرسی از دعوتتون. خب گوش دادید. ممنون.